So you know how angular momentum works because of Isaac's first law of inertia. It explains why things move in a circle, not in a straight line, and they don't get pulled into the center of rotation. So let's say this is your center point of rotation, and there's a ball on a string like this, and that's the ball, and it's being like thrown in a circle. Well, I'll make the center point a little closer to the center. So yeah, it's being rotated this way. So this ball will feel it when it's traveling in a circle. It's always gonna feel this outward push, kind of, just like when you're in a car and you make a turn. It seems like your body gets pushed to the outside of the car, but really what happens is any mass, anything that has mass has inertia. So when it's being rotated and it's turning, its body's inertia will continue to make it want to go tangential to its radius like this. So this will be a 90-degree angle right here. All right. So at any point on the circle, whether you're here, 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 it's always gonna be tangential. All right, 90-degree angle here. Let's just do this one real quick. All right, so this is what is called tangential velocity. So at this point, how let's use this point again. This vector represents an object's tangential velocity, and it basically means that, well, I'll do a quick example. If this were a string and it was cut right here, and the ball was just let go and it could freely move now, it would continue to move this way at a certain speed. So let's say that speed is 2 meters per second, just for example. That would be its tangential velocity. And inertia explains that because any body's inertia will make you want to continue to go the same direction that it was moving before. So talking about an object's tangential velocity and inertia, we can calculate an object's rotational inertia. Just put the mass there. We can calculate a object's rotational inertia or moment of inertia using this following equation. So you have I, which is the inertia, equals r squared. R standing for the radius, and m standing for mass, representing mass. Alright, so first, to understand angular momentum, you will need to understand regular linear momentum, which is when things move in a straight line. So, linear momentum is defined as P equals mass, the M for mass, I'll write that, times the velocity. Alright, so this is linear momentum. So when you're calculating angular momentum, you're going to have the radius, which is this distance right here. That's the radius, the r, the distance from the center to the outermost point of the circle, times the linear momentum. So when you have a situation like this object right here will probably have some mass. So this will have some mass. And when you're finding the linear velocity, the linear momentum of this object, you're going to take the tangential velocity. So that at any given point on the circle, the object is moving perpendicular to the radius, like this radius line right here. So it's moving this way. Well, the velocity is this way. So like that. So you're going to take the mass of this, times the velocity. And that is going to be your linear momentum. So let's do an example. So let's say you have this object right here going counterclockwise on a string. Let's assume the string is massless, and it's fixed to the center point right here. So this will be your radius, the distance from your center point to where your object is. So let's say the object is 5 kilograms, and its tangential velocity is 6 meters per second, and your radius is 4 meters. So first, what you probably want to do is find your linear momentum, right? So you're gonna do P equals 5 times 6. Well, let me label these. 5 times 6 meters per second, and that will give you 30 kilograms times meter per second. All right, and that is your linear momentum. So now you're going to take your linear momentum and you're going to multiply it by your radius. So you are going to take 30 and multiply it by 4. And that will give you 100. Can you pause it real quick? And 120 will be measured in kilograms times meters squared over seconds. So let's do an example. So we're gonna we're gonna be figuring out the angular momentum of the Earth in relation to the Sun. So it orbits around the Sun in the circular path. We're just gonna say that's how it is. All right, so we have the mass, which is 5.92 times 10 to the 24th kilograms. Velocity, its tangential velocity, once again, which is this way, is 30,000 meters per second, and its radius is 1.4 times 10 to the 11. So first, let's find its linear momentum. So we're gonna take the mass, 0.92 times 10 to the 24, and multiply it by its velocity, which is 3 times 10 to the 4th. All right, so 5.92 is pretty close to 6, so I'm gonna act like it is 6, and I'm just gonna round. So it's gonna be about 1.8 times 10 to the 29th. Just did that on my head real quick. Okay. Let's get kilograms times meters per second. I don't like that. That's bothering me. Alright. And that's its, alright, P there. That's its linear momentum. So, to find angular momentum, we're going to take the linear momentum, 1.8 times 10 to the 29th, multiply it by, put parentheses, 1.4 times 10 to the 11th. And it's going to be pretty close to about, I'm just going to kind of round again. It's going to be close to 10 to the 40th. and that's its angular momentum of the Earth. Alright, so let's do a real life application problem. Well, something that can be related to real life. So NASA wants to send a rocket into space. They want to calculate its angular momentum as it leaves the Earth's orbit. So we have escape velocity, which is the velocity that it will be traveling at. And that is 4 times 10 to the 7th meters per second. The mass, which is 3 million kilograms, and the radius that its orbit is away from the Earth, which is 100,000 meters. So let's say this is the Earth, and this is the orbit that it travels. I mean, 100,000 meters is probably higher than that, but we're all right. So it gets launched this way. So it goes around the Earth one time, and it gets launched tangentially out this way. So escape velocity is 4 times 10 to the 7th, which means at this point right here, it will be moving this way at 4 times 10 to the 7th meters per second. Alright, so let's find its linear momentum. So we're going to take 4 times 10 to the 7th and multiply it by 3 times 10 to the 6th. Alright. And we're going to get 1.2 times 10 to the 14th times meters per second. Alright, so that's our linear momentum. So let's find angular momentum. So basically we're going to take the linear momentum and multiply it by the radius. So we have 1.2 times 10 to the 14th times 10 to the 5th. Alright, and it's going to be 1.2 times 10 to the 19th. Let me just make sure I did that right. And yeah, looks good. Yeah. And that's going to be your angular momentum.